we last left off when we had calculated the radius of the electron orbit based upon the Bohr version of the model, that it went from the electrons in a, like I say, pudding of positive charge to having a nucleus and electrons going around it, to now Bohr saying that electrons can exist only at certain levels. And he had the radius a sub naught. So the radius of an orbit is a sub naught n squared, where a sub naught is 5.291771 times 10 to the negative 9 meters. Is that the answer what we had last time? Is that a yes?
I don't have that.
Yeah, I don't either.
I have 5.3 times 10 to the negative 11.
You have 3 times 10 to the negative 11th.
5.3.
5.3 times 10 to the negative 11th. Let's see, so. Oh, yeah, sorry. I had it in terms of 0.5, in essence, 0.53 times 10 to the negative 10th, and then I went the wrong way. Okay. Recognize that this is 0.53 rounding off angstroms. The angstrom being the unit basically set up so that the size of an atom is 1-ish. All right, so the energy. Still going in sort of that planetary model. Well, first off, what comprises energy? What are my 2 types? Assuming the electron is not going to burst into flames.
Potential.
And
Kinetic.
oh, 3 of you have had me before, and Christopher should know it also. But what's the formula for kinetic energy?
1/2 mv squared.
Now that's supposed to be a cue for everyone to do it in unison. But thank you. So that's mass of the electron times the speed of the electron in its orbit, and then the potential energy. What's the formula for potential energy?
What kind?
Thank you. The one associated with the electric force. And the answer to this would have been in sometime in January of this year. The electric potential energy.
I have the K times Q1, Q2 over R.
Okay, and there's the formula. Now, for the sake of simplicity, let's just assume that we're dealing with a hydrogen atom. So I just got a proton in the nucleus and I got an electron zipping around it. So minus, because one's an electron, one's a proton, minus K, and I'm going to go to the more traditional 1 over 4 pi epsilon naught, E squared over R. The E in this case is the base charge of an electron or proton, 1.6 times 10 to the negative 19. And just to give you a sense of how on top of there I am today, I was doing a demonstration in an earlier class, had a tuning fork that I was just using, and then about 30 seconds later I couldn't find the tuning fork that hadn't moved from its position from when I just used it. So, I'm on top of my game right now. Oh, I was watching the very end of what we did in class last week, and I made a reference to the radius of the electron, and it really is, that's the radius of the electron orbit, not the radius of the electron itself. As I'm sure all of you remember, because, well, one, I said it, therefore you remember it, and two, I'm sure you've watched the video over and over again. Brought friends over, just rejoiced. All right, so if I've got my nucleus here, or actually proton in my nice simplified model, and I got an electron zipping around it, what kind of orbit are we talking about? What's the motion? What's the adjective that describes the motion of something in circular orbit? We have covered it in this class, but it's mainly a 251 topic.
Angular.
Okay, not the one I was thinking of.
Centripetal.
That's the one I'm thinking of. What's the force acting on the electron?
The electric force.
All right, pointing towards the center. That's the K Q1 Q2 over R, or 1 over 4 pi epsilon naught Q1 Q2 over R. So let's just do a little plug and chug there. So I have my force, 1 over 4 pi epsilon naught times E squared over, that should be R squared, is equal to mv squared over R. Guess we'll unplug this till I'm ready for it. So if I solve for mv squared, I get 1 over 4 pi epsilon sub naught E squared over R. And if I want the 1/2 mv squared, in other words, the kinetic energy, I'll just multiply both sides by 1/2. So in essence, what I have here is my kinetic energy for something in orbit is just half the magnitude of my potential energy. Or I guess properly, half the absolute value of my potential energy. So we end up with half of this minus this, so we end up with negative 1/2 over 1 over 4 pi epsilon sub naught E squared over R. And for something in orbit around some central body from gravitational force, it'd be the same thing, except it'd be big G up front and the product of the masses. And typically, when you have something orbiting, the total energy is negative. This is right here. All right, so that's my total energy right there. I also know that I have a value for my radius over there. So negative 1/2. Let's go ahead and combine those. 8 pi epsilon naught E squared over R, and the formula for R we had last time. Four pi epsilon naught H bar squared over mass times the charge squared n squared. And again, n is just some counting number. And we end up with negative 1 over 32. That's not 0.8, that's 8. .32 pi 32. Pi squared epsilon naught squared h bar squared times mass e to the fourth power times 1 over n squared. What's that equal? I'll do a quick check to make sure I didn't do something silly here. 32 naught squared, bar squared. Okay, yeah, we're good. Mass of the electron? 9.11 times 10 to the negative 31st kilograms. H bar is h over 2 pi, which is 6.626 times 10 to the negative 34th joule seconds over 2 pi. E, 1.6 times 10 to the negative 19th. Obviously not. Only where's E? Epsilon sub naught. 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. And that's it. So what do we get? Who's gonna be brave enough to do it first?
Well, my calculator keeps going to 0 when I do e to the fourth,
It's too big of a function for us.
so I have to do the denominator first to make it a bigger number.
When you do what to the fourth?
The charge of the electron. It automatically goes to 0.
I guess it just rounds to 0.
Huh.
Yeah.
Well, let's do that part, let's do them separate then. So, in terms of exponents, I have 10, so just do the, I forget what it's actually called in math, but just do the number in front.
I got negative 5.299 times 10 to the 38.
10 to the 38th. That seems awfully huge.
Yeah.
All right, so we have, so if you do the other numbers, I'll do the times 10 to the negative 31, 10 to the negative 19th, the fourth power, over just regular numbers. I got 10 to the negative 12th squared, 10 to the negative 34th squared. So that's 76. 31, so 76 and 31. 107.
I think it's.
And then negative 24, negative 68, negative 92. So I'm getting negative 10 to, something times 10 to the negative 15.
negative 2.17 times 10 to the negative 18.
Negative 2.17
Yeah,
times 10 to the negative 18
yes.
units.
1 over n squared.
That, whatever n squared is unitless.
N over coulombs.
What did we just find? What quantity?
Energy,
Units are?
joule.
Yeah, joules. Over n squared. Now, doing it the other way, for the calculators that couldn't handle it, I'm assuming therefore you got 0.00217 when you did 9.11 times 1.6 raised to the 4th divided by 32 divided by pi squared divided by 8.85 squared divided by 6.625 squared times 4 pi squared.
Me?
No, others.
Oh.
Whose calculators couldn't handle it. I will take that as a yes. Anyway, what Sarah said matches what I had written down, so we either both made a careless error, the same careless error, or it is right. Now, dealing with energy levels that small, typically you don't deal with joules, so you deal with something that is, well, where you're not dealing with such huge exponents. So let's put it in terms of electron volts, which is another unit of energy. And to do that conversion, I've got negative 2.17 times 10 to the negative 18th joules times 1.6 times 10 to the negative 19th joules per electron volt. An electron volt is the amount of energy an electron would gain if it went through 1 volt of potential. Or potential difference, I should say.
$13.565.
13.565.
565.
In chemistry, I don't know if you remember this. I remember seeing it, negative 13.6 electron volts. Does this ring a bell from? Okay. It was one of those numbers I remember seeing, and then it never really explained where you get it. But so if later on you're taking a chemistry course, you know, for evidence of something you've done wrong, and 13.6 comes out. This is where it comes from. So the energy level. We'll stick with joules. It's going to be negative 2.17 times 10 to the negative 18th joules times 1 over n squared, where n is the basically the orbital number. And that first number is a 2. That is a 7. So, how much energy does it take for an electron to move from the first energy level to the second energy level? Well, simple enough to find. To go from energy n equals 1 to energy n equals 2, well, the amount of energy it needs is the difference. So this would be E2 minus E1, which is negative 2.17 times 10 to the negative 18th joules, times 1/4 minus 1/1. 2 squared and 1 squared. So we end up with So, if that's the amount of energy, what is the frequency of light that would produce that? Well, I know that if that's the amount of energy required, so I have light coming in with that amount of energy, I know energy of the electromagnetic wave is just HF, Planck's constant times the frequency. We can solve for the frequency. So the frequency of light coming in, we have 1.6275 times 10 to the negative 18 joules divided by Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds. And we end up with
2.456 times 10 to the negative, or 10 to the 15.
units,
Is that per second? Hertz?
hertz, yeah. Now typically when you're talking about electromagnetic radiation, yeah, there are some venues where you would use frequency, but usually if you go to the tables, they give it to you for wavelength. So let's take a look at the wavelength that is associated with that. I know that the speed of a wave is equal to the frequency times the wavelength. So the wavelength is the speed divided by the frequency, which is 3 times 10 to the 8th meters per second, divided by 2.456 times 10 to the 15th hertz.